So again, taking some lessons from cryptographic protocols, we want to make sure that we get a fresh result here. And so instead of just saying, look, compute this checksum over your memory contents and return the same answer every time, this time we're going to include a challenge of some kind. So the checksum function that's computed over memory is going to not just depend on the contents of memory, but also on the challenge that comes in from the verification device. So that at least the malicious code in this case is going to have to perform a computation to take into consideration the challenge. But unfortunately, this is still a vulnerable solution. If there's unused memory, a slightly modified checksum function could conceivably return the same result, or rather the correct result, despite the memory contents having a problem. So that's a basic introduction to what we'd like to do with software-based attestation. You know, it's attestation just like with the hardware scenario, but we don't have hardware support. We're going to construct this special verification function that's going to let us get these desirable properties that a precise piece of code executed, even in the presence of malicious code. And so we're going to move forward by discussing the history of software-based attestation mechanisms and see how the state-of-the-art today has been developed. Some of the systems that we're going to discuss are SWAT, which was software-based attestation, a SWAT verification function. Then a system called Pioneer, which takes that a few steps further and actually gives you this externally verifiable code execution property. And then we're going to talk about some applications of this stuff and some open research challenges. There are indeed many open research challenges in this space still. So I'm going to skip some of these because I'm not an expert on that first one. So looking at the verification function in the third bullet there, the idea is that we know something about the hardware platform that we're going to interrogate. So the target platform that we're trying to make a trust decision on, assume that we have very detailed knowledge of its CPUs, capabilities, speed, cache sizes, everything you might need to understand the performance of that system. If we somehow filled memory with random content, and we somehow get the CPU state into a well-understood state, so cleared with interrupts disabled so that it's going to do some straight-line execution, then maybe we can compute the hash over the entire memory contents and return the hash value and system state to the verification device. The verifier is not only going to check that the values returned are correct, so clearly the hash value needs to be the expected hash value, otherwise we assume memory contents have been modified. But that's the thing that hackers, or rather attackers, are fairly skilled at trying to achieve. The more interesting thing is the duration of this operation. So because we have this detailed knowledge of the hardware architecture, we can make an analytical conclusion on how long it should take for this set of hash functions to execute. And so if the attacker is going to somehow return the correct answer, he's going to have to do some extra work. And that extra work is going to result in the duration of this computation increasing. And so the verifier has actually two responsibilities. One, it needs to make sure it gets back the right answer. And two, it needs to make sure it gets back the right answer in the expected amount of time. So Genuinity was an example of a system that was exploring this space. I think that the particular nuances of its verification function aren't necessarily critically important to us here today, but they made the argument that it is difficult to simulate the precise set of operations that they were executing because simulation or emulation, as opposed to just virtualizing the execution of some things, can induce higher overhead. And so their system was kind of, at least my understanding of it, is that it was engineered based on this intuition, that simulating this can be really difficult. But it turns out after a while that there were some weaknesses in the particular function that they put together, and that there are clever ways to simulate the operations that it wants to do. And so while this system, I think, is an interesting milestone, the particular algorithm proposed has some flaws. So I think the next step or the next iteration in the development of these mechanisms that's interesting is that we want to fill the entire data memory with random uncompressible contents. So if you think back to some of the attacks I mentioned a few slides ago, the attacker depended on the existence of some unused memory, some memory that had zeros in it, so that it could store either a copy of the intended code or at least its malicious executable. It basically needs a place to execute where it can hide. And one way to think about unused memory is just that it's highly compressible and that its value is supposed to be 0. So whenever anything's in that address range, it returns 0. So the contribution here is that if we fill the entire memory, the unused memory included, with pseudo-random uncompressible contents, then there's no room left for the attacker to insert their arbitrary code. And it actually turns out, I think, that their best bet ends up being trying to compress legitimate program code. So this is an interesting example, a relatively recent result. So the idea is that they have a very simple program that's basically designed to print out the contents of memory. And again, based on this assumption that we understand our hardware very well, so the length of time that it should take to print out the entire contents of memory can be anticipated. And so when you execute this program, you watch the production of the output. If the output's incorrect, you cry foul. If it takes too long, also cry foul. My understanding of the contribution here, and again, I'm not 100% certain of this, but that is that this is a simple enough model that you can start to do some formal reasoning about exactly what properties this program achieves. So one of the things I haven't really mentioned yet is that it's valuable to do these memory traversals in a pseudo-random pattern. I think we're going to get to that in a few slides, so I'm not going to go into it right this minute. But when you do this pseudo-random pattern, it becomes more difficult to reason about exactly what the expected execution time is, because there's a little bit of a statistical distribution on whether you're going to have a cache hit or a cache miss. I think we'll get to that in a few slides.